In 2015, a star 1,470 light-years from Earth did something that no star in recorded astronomical history had ever done before. It dimmed by 22% in a matter of days. Nobody knows why. The star sits in the constellation Cygnus, embedded in a dense corridor of the Milky Way that the Kepler Space Telescope spent 4 years staring at without blinking. Kepler was built to find planets by watching for the faint, regular dimming that happens when a planet passes in front of its host star. A planet the size of Jupiter blocks roughly 1% of the light from a sun-like star. The signal is subtle. The pattern is predictable. The dimming profile is smooth and symmetrical, shaped by the clean circular geometry of a sphere passing across a disk. This star produced none of those things. The dimming events Kepler recorded were irregular. They came without warning and without a fixed schedule. They lasted different amounts of time. Their shapes were asymmetrical, the star's light sometimes dropping sharply on one side and recovering slowly on the other, or dipping in complex staggered patterns that suggested not one obstruction, but many moving in loose and unpredictable formation. And the magnitude of the dimming was unlike anything in the Kepler dataset. 22%, not 1% or 2%. An obstruction capable of blocking that much light from a star would need to be nearly twice the diameter of the star itself. Nothing in planetary science, nothing in the 4-billion-year history of solar system formation produces an object that size in orbit around a single star. The star was named after Tabitha Boyajian, the astronomer who led the team that first analyzed its behavior. She had been working through data flagged by citizen scientists, volunteers combing through Kepler's output looking for anomalies too complex for automated systems to classify. They had marked this star as unusual. When Boyajian's team looked closer, unusual turned out to be a significant understatement. The scientific community's first instinct was to find the simplest possible explanation. A swarm of comets seemed promising at first. A dense, fragmented cloud of icy bodies passing between the star and the telescope could, in principle, produce irregular dimming. The hypothesis was coherent, and for a brief window it appeared to fit the optical data. Then the infrared measurements came back. Any dense collection, sommaire, of solid or icy material absorbs starlight and re-radiates it as heat. It produces a clear, detectable excess of infrared emission, a thermal signature that scales with the amount of blocking material present. If something large enough to dim a star by 22% was orbiting Tabby's star, the infrared data should have been unmistakable. The star showed no infrared excess at all. The simplest explanation collapsed. The scientific community moved to the next candidate. A planetary collision, a catastrophic impact that had filled the inner system with a thick, expanding cloud of dust and fragments, could theoretically produce irregular, asymmetrical dimming without requiring a single, impossibly large object. This hypothesis also made predictions about the infrared. The infrared data returned the same answer. Nothing. By this point, the star had accumulated a second layer of strangeness. Researchers going back through historical records, glass photographic plates taken at the Harvard College Observatory beginning in the 1890s. They found something the original Kepler analysis had not been designed to look for. Tabby's star had been fading. Not just during the dramatic dipping events, but continuously over the entire span of the historical record. From the earliest photographic plate to the most recent, the star dimmed by approximately 14% over roughly 100 years. This is not how stars behave. Stars of this type, F-type main sequence stars slightly larger and hotter than our own Sun, do not simply fade over a century. Stellar evolution operates on timescales measured in hundreds of millions of years, not hundreds. There is no known mechanism in stellar physics that causes a mature main sequence star to dim at this rate, without producing other observable changes in its spectrum or its structure. The century-long fade had no explanation at all. It did not fit any of the hypotheses proposed for the short-term dipping events. It was a separate anomaly, sitting beneath the first one, with no obvious connection to it. The question deepened again in 2017, when a coordinated international observation campaign watched the star in real time as one of its dipping events unfolded. For the first time, astronomers measured its behavior across different wavelengths of light at the same time. Wavelength-dependent dimming is a diagnostic tool. A solid, opaque object, a planet, a rock, or a dense fragment of debris blocks all wavelengths equally. It simply gets in the way. But dust, gas, or some other diffuse medium scatters and absorbs different wavelengths at different rates. If the dimming is stronger at some wavelengths than others, the obstruction is not solid. It is something finer. The 2017 campaign confirmed that the dimming depended on wavelength. Short wavelengths were blocked more strongly than long ones. Whatever passed in front of the star was not a planet, not a fragment, and not a coherent piece of debris. It was fine material, dust perhaps, or something with the optical properties of dust, but interstellar dust does not produce the correct dimming profile, and it does not explain a 100-year fade. The wavelength data narrowed the field of candidates and opened a new gap at the same time. What could produce wavelength-dependent dimming on a scale 20 times larger than a planetary transit in an irregular and non-repeating pattern, while simultaneously causing a star to lose 14% of its brightness across a century without producing any detectable heat? No hypothesis currently accepted by the scientific community answers all four of those questions at once. Some researchers have proposed that the century-long fade and the short-term dipping events might have separate causes, two distinct and unrelated processes occurring at the same time. This interpretation is uncomfortable. Science tends to prefer unified explanations. Two independent anomalies in the same system requires accepting an improbable convergence. But the alternative, a single mechanism that accounts for the dips, the fade, the wavelength dependence, and the absence of infrared emission, has not been identified. The strange thing about Tabby's star is that the look elsewhere effect does not apply to it. The anomalies here are not marginal excesses at the edge of statistical significance. A 22% dimming event is not a subtle artifact. 100 years of continuous fading is not noise in the data. They are the loudest things in the room. Tabby's star has been studied intensively for more than a decade. The results are consistent and reproducible and deeply strange. What produces the dips has not been identified. What produces the century-long fade has not been identified. No model accounts for all the observations simultaneously. The star is 1,470 light-years away. The light arriving at our telescopes tonight left that system somewhere around the year 550. Whatever is happening there, whatever has been dimming that star since before the first photograph was taken, whatever passed in front of it in 2015 and blocked a fifth of its light, has been happening for a very long time without a name. It is still happening now.